You're moving at 20% of light speed when the warning appears. Object ahead. Range 1 million kilometers. Time to impact 17 seconds. You won't see it. The grain is microscopic and almost black. By the time a sensor is certain, physics has already chosen the ending. 16 seconds. You can't turn hard enough, and you can't ask Earth for help. Its answer would arrive years after the collision. 10 seconds. The grain has no engine, no guidance, and no idea you're here. Somehow, it is still winning. Contact. The grain and part of your forward shield flash into plasma. A crater opens. Thermal energy moves through the layers below, toward electronics carrying 20 years of observations and an appointment with another star. That was one grain. Interstellar space is extremely thin, but you're crossing it at nearly 60,000 kilometers each second. At that speed, sparse gas becomes radiation and dust becomes a hypervelocity impact problem. The velocity that makes this mission possible also turns the road against you. For the rest of this mission, we're building one spacecraft. We'll call it Needle. Its target is Alpha Centauri, a little over 4 light years away. The plan: cross the gap, perform one flyby, then send data home. At 0.2 C, the cruise alone takes just over 20 years. Acceleration, navigation, communication, and braking come separately. NASA's Parker Solar Probe has reached about 700,000 kilometers per hour near the Sun. That record comes while diving through the Sun's gravity well. Parker cannot take the next exit to Alpha Centauri. Even if it could cruise in the right direction at that speed, the journey would take thousands of years. Needle must go much faster. One well-studied approach starts with gram-scale electronics on a reflective sail, pushed by a powerful beam built in the solar system. Low mass makes acceleration easier. It also leaves almost no room for fuel, repairs, redundancy, or armor. We have solved propulsion by giving the spacecraft roughly the luggage allowance of a postage stamp. Needle reaches cruise speed, and the environment changes. The space between stars contains mostly hydrogen and helium, plus heavier atoms, cosmic rays, and dust. It is sparse, but impact energy depends on closing speed. Gas atoms can heat and scar the forward surface. Heavier nuclei can cut tracks through some materials. Dust delivers much more energy to one tiny spot, melting, ionizing, and excavating the shield. Published models estimate cumulative damage, not a universal forecast. In one small probe analysis, at 0.2 C, gas produced about 1/10 of a millimeter of track-forming damage in quartz. Under another stated column density, dust removed roughly 0.5 millimeter from the leading surface. Graphite behaved differently. Root, geometry, and dust assumptions matter. Still, 0.5 millimeter matters when the probe may be only centimeters thick. A spherical silicate grain with a radius of 1 micrometer, assuming a density of 3,000 kilograms per cubic meter, carries about 23 joules at 0.2 C. Make its radius 10 times larger and its mass rises 1,000-fold, giving roughly 23 kilojoules. Such grains should be much rarer. This does not predict how often one appears. It does explain why Needle's nose has become the fastest sandblaster target ever designed. Our first defense is geometry. Needle becomes long and narrow, exposing as little frontal area as possible. Tough, sacrificial material sits ahead of the electronics. We expect the journey to eat it. That may handle gradual heating and erosion. A larger grain can dump energy too deeply and too quickly, so we need to spread the impact before it reaches the body. One proposal places a thin foil ahead of the craft. A grain strikes the foil first, breaks apart, and expands into hot fragments in plasma. The main shield still takes the energy, but over a wider area. Electric or magnetic fields may steer charged fragments and incoming ions away from sensitive hardware. Neutral dust is less helpful. It must be ionized before a magnetic field can redirect it. Magnetism is impressive, but it cannot negotiate with an object that has declined to be charged. The foil helps. The field helps. A thicker shield helps. All of them add mass. More mass demands more launch energy and larger infrastructure. Every gram we add hurts acceleration. Every gram we remove hurts survival. The shield has handed its bill to propulsion. Perhaps Needle can dodge the worst grains instead of absorbing them. The timing is ugly. At 0.2 C, an object 1 million kilometers ahead arrives in about 16.7 seconds. That sounds generous, until the object is microscopic and almost black, while the detector is riding on a gram-scale probe. An avoidance system must find the grain, decide whether the signal is real, calculate a maneuver, and move Needle far enough sideways. Meanwhile, the gap shrinks by almost 60,000 kilometers every second. We cannot safely assume detection of ordinary tiny grains at that range. So the mission needs a different defense. Assume that some impacts will happen. We can distribute components so one impact does not destroy everything, then launch a swarm instead of trusting one craft. If some probes fail, survivors may still finish the mission. The swarm creates its own trouble. Every probe needs power, instruments, autonomous navigation, pointing, and a transmitter that can reach Earth across 4 light years. More probes also mean more launches and tracking. We made Needle tiny so we could accelerate it. Now each copy must work as pilot, mechanic, scientist, and deep space radio station. The spacecraft stayed gram scale. Its job description did not. Suppose Needle survives and reaches Alpha Centauri at 0.2 C. Reaching the system does not mean the probe has arrived. It has started a very brief encounter. At that speed, one astronomical unit takes under 42 minutes. Targets move, cameras need exposure time, instruments and antennas must point accurately while Needle tears through a system it has never seen up close. Earth cannot help. A command needs more than 4 years to arrive. Needle must choose targets, react, collect and store data, survive the pass, then aim a signal toward a faint point near the sun. This becomes a drive-by science exam followed by a 4-year wait for anyone to grade it. Slowing down opens another problem. A rendezvous mission must lose almost all its cruise velocity. Ideas include a destination beam, magnetic or electric sails, onboard fusion, and speculative antimatter-assisted systems. Some have received early study. None is ready for installation. A destination beam requires infrastructure that does not exist there. Onboard propulsion adds mass. A sail needs the right environment and must survive deployment. Reaching another star and stopping there remain 2 different inventions. Needle is fragile, but at least it doesn't breathe. A mission carrying people needs pressurized living space, water, food, recycling, medical equipment, radiation protection, spare parts, and systems that work for decades. Its shield has a far larger cross-section because the crew cannot be folded into a wafer. Take a hypothetical 1,000 metric ton ship at 0.2 C. Its crew's kinetic energy is about 1.85 times 10 to the 21 joules, equivalent to roughly 443 gigatons of TNT. That is not the energy required to run the whole mission. It is only what the moving ship carries. Real propulsion wastes energy, and braking needs another answer. The shield grows. The propulsion system grows to accelerate the shield. The habitat grows to support the people maintaining those systems. Redundancy adds more mass because a crew cannot be treated as a disposable member of a robotic swarm. What are they traveling toward? Proxima Centauri b is the nearest confirmed exoplanet and roughly Earth mass. But mass alone does not make it a second Earth. Its atmosphere and surface conditions remain uncertain, and its star is unlike the Sun. Calling a planet Earth mass describes its mass. It is not a hotel review. Telescopes may tell us more before anyone launches a crew. The design has reached an awkward result. Our probe accelerates because it is tiny, which makes it fragile. Armor punishes acceleration. A swarm spreads risk, but every probe works alone. A flyby avoids braking and squeezes the encounter into minutes. People enlarge every trade-off. None of this proves interstellar travel impossible. The estimates depend on materials, assumptions, and uncertain dust. Better technology could move every boundary. Physics has not hung a closed sign between the stars. Instead, physics lists the cost. If we send a purpose-built craft toward another star in the foreseeable future, it will likely be robotic. It may travel as one member of a swarm whose designers expect losses. It may accept a fast flyby rather than carry the machinery to stop. Even after a successful encounter, its first close observations will need more than 4 years to reach us. Needle's final act is not a landing. It turns home, finds the sun, and transmits with whatever power and hardware the crossing left intact. The first interstellar traveler may be a camera wrapped in armor, too fast to stay, too distant to rescue, and carrying an answer we will wait years to receive. The space between stars is vast, but distance is the quiet problem. Danger begins when we try to cross it quickly, and empty space stops behaving like emptiness.